Hi, everyone. My name is Muriel Médard. I'm co-founder, CEO of Optimum. I'm also co-inventor of some of our underlying technology, randomly network coding. And today I'd like to walk with you about how it works and also comparing it to what happens when you have no coding or when you have old-fashioned 1950s, 1960s coding like Reed Solomon. So this is what we're going to be looking at together today. It's Optimum's protocol visualization. It's an interactive explainer, a visualization to see how these different propagation strategies behave in a mesh network that has bandwidth constraints. Just to be upfront, this isn't a benchmark, this isn't a live system. It's really an intuition building tool so that we can understand very directly how these different systems work. The purpose behind building it is so that anyone, our community members, engineers, partners, can see right away why the coding strategy you choose really matters in a crucial fashion. So here's the problem I want you to see. Every node in a network, what we often call a mesh, a richly interconnected network, has a limited inbound bandwidth budget. And we have to work around that budget. Now, one of the things that impacts that bandwidth budget is when in a system like you would have, say, in Ethereum, peers, those are to say nodes inside a network, are sending redundant or duplicate data. If you're sending wasteful data, that's the same thing as effectively having less of a budget, less bandwidth. So it's not just the bandwidth that's there, but how you use it. If you're wasting it, it's the same as having less bandwidth. And having less bandwidth means that nodes are going to take longer to actually get the data, and that's taking longer to get the data is going to impact what happens with respect to speed, latency, and general performance of the system, of the protocol. So the central question that I'm asking in this first landing page is the following. How do we keep every inbound connection doing work that's useful? How do we not waste those bandwidth resources? And to do so, we're going to compare side by side three main protocols. One is without coding. This is my baseline. This is what's happening right now, saying something like Ethereum with libp2p, source forwards original shards directly, and the duplicates pile up really fast. Nodes have to become therefore selective about which peers they listen to so that they don't basically drown under duplicates. And then there's limited forward movement of the data to avoid that drowning, and that limited forward movement of the data is itself deleterious and something that we didn't really want. Reed Solomon is a middle ground that's using a system that was developed for an entirely different approach, way before I was born. And there, the source encodes a message into 64 shards, and any 32 of those suffice to actually do the reconstruction. So more arrival state useful. And at first it would seem like, okay, this is going to really manage the issue of the overlap or the duplication. But it turns out that it's really limited by the fact that you have to make that assignment of 32 to 64 shards in a really static fashion. And so particularly as the network grows, that becomes actually almost as bad as without coding. So it's not as bad as without coding, but it really is inherently having the same limitations as without coding. The last one, randomly network coding, which I'm co-inventor of, as I mentioned earlier, is the one I really want you to focus on. That one is built for this kind of networks. It's not built, a lifetime ago for something completely different. This is built basically with these decentralized systems in mind and is optimum for these decentralized systems. What happens here is you have these shards from different peers that are not just coded at the source, like with Reed Solomon, but are being recoded as we go along so that the inbound bandwidth is always staying productive. Okay, so here's how the visualization works. All three parts are going to run simultaneously under identical conditions. Same topologies, as to say the same shape of the network, same connections, same inbound capacity, and same connectivity, so about 3 to 5 peers per node. Same playback speed for all three. So each node is showing a live badge with its inbound slots. Nodes are changing from gray to green when they decode, that's to say, when they get the data that they need, and edges light up in each protocol's signature color as packets are flowing. At the bottom of each panel, I'm tracking three live metrics: helpful inbound peers, the bandwidth used, and the decode time. You can pause at any time and click on a node to inspect its active inbound peers if you want to deep dive on exactly what one of the nodes is doing. So, what is here the punchline? What do the numbers say? When the run completes, the numbers tell the story clearly. And this is what we just watched happen. Without coding, you can see how many seconds it took to decode, and you can see how much of the bandwidth was useful. So here you can see that you take about 7 seconds to decode, and the bandwidth consumed was basically around 10,000 units of bandwidth. If you look with the Reed-Solomon, you can see that the decode was shorter. It was about 1.75 of a second. You can see that the bandwidth consumed was somewhat lower, but not massively lower, about 7,000 units basically in terms of these shards that were sent around. And now let's look at RLNC. We're looking at 171 milliseconds. That means that's 0.17 seconds. That's about 10 times faster than Reed-Solomon. And the amount of bandwidth consumed is much smaller. So you can see that the bandwidth consumed here is about, say 12 times smaller than without coding, about 7 times smaller than with Reed-Solomon. And this is why Reed-Solomon, even though it's a code, is still a highly suboptimal code. So you're seeing that the single point I want to take away from this is, in a constrained mesh network, the bottleneck isn't just the raw bandwidth. It's how you're making use of that bandwidth. And how you're making use of that bandwidth depends on how judiciously you're using it and how much redundant, useless information you're sending. RLNC keeps every inbound link useful. That's what we're building Optimum around it. And I'll say it plainly, the page says it too. This is an intuition tool, but it's a really valuable intuition tool. So please play with it, check it out, and give us feedback and send us any comments, suggestions, and questions you may have. Thank you very much.